Good morning, children. Today we are talking about the magnetic effects of electric current, and I got a bar magnet here, and as I move the bar magnet you can see the lines of force because compass arranged at different locations and how a compass behaves, and you can see the way these compasses, tiny compasses line up. We can understand the lines of force, they never intersect each other because at the point of intersection the direction of magnetic field will have two different directions, which is not possible, and therefore lines of force all the time they start at the north pole and they move towards the south pole. We also have learnt that it's as an imaginary path traced, when an isolated north pole is left there, either it moves or tends to move in that particular direction, and that is what we mean by line of force. Okay, having done that, of course I can take a compass and check. Okay, this is south pole and here you have north pole, and they are opposite poles, they are attracting each other. And when you bring the same compass here, and this is north pole and this end is south pole, the white one, and they are attracting each other. For the time being I just keep it aside, and when I move the magnet you can see the magnetic field also is changing. Okay, this is what we should understand. It is the first point. The next one is I am taking a pickup coil. See, this is just a coil, and there is no source of energy in that. It's connected to a bulb. Okay, that's what we exactly have. And what for do we use this actually? Like in case there is a current flowing in this coil, and that bulb can glow, and how does the current flow in that, because there is no source of energy. But however, when you have a magnet here and try to understand, this magnet has got a magnetic flux. Okay, and when the magnet is moving towards the coil, the magnetic flux is changing. Okay, whether the magnet is coming backwards or whether the magnet is coming towards the coil. So let us understand actually when it's moving fast, rate of change of magnetic flux, and that is going to produce EMF. More is the rate of change of flux, of course, d phi by dt, like it's more of induced EMF you have there. So when it is moving fast, so naturally the current is produced, which eventually is making the bulb glow. And in case you want to check whether the current is passing through this coil or not, you can in fact have a galvanometer also. Like now we have a galvanometer, and when you move it this side, it is deflecting to one side, when you are moving back to the other side. So when you are moving the magnet inside the coil, you can see the deflection on either side of that. So that tells you that there is a current flowing, a current generated when like magnet is moved in the coil. So this is a very important point we need to use in this magnetic effect of electric current, because this is the relation between magnetism and electric current. Okay, when a magnetic flux is changing near the coil, current is induced in the coil. That is what we need to understand. But however, if you have current in the circuit, automatically a magnetic field is developed. This is in contrast with what we have learnt now. Imagine for some time, okay, there is a coil which is connected to a DC source here. So automatically there is a magnetic field developed. When current is flowing in the coil, magnetic field is produced around it, whether it is a straight conductor or a coil. In either case, what happens is there is a magnetic field developed around it. So you are not seeing anything that's happening here like substantially. But here I just want to tell you something more interesting here. See, this is a DC current, therefore you don't find any kind of change in the magnetic field when current is passing. This is a DC current. But instead, if you have AC current, and where I can change the frequency also, you can see the magnetic field is continuously changing. And this is for the reason the induced EMF, the current is flowing in both the directions. And therefore, the current is reaching the peak and there is no current and it's moving in the opposite direction. So eventually, if you draw a graph taking current and time, and you get a sinusoid wave, like a sine wave you will get. So this is AC current. Okay, you may not get an opportunity to learn about how you have the magnetic field changing when like AC is used, but generally we talk about DC, where the current remains the constant. Okay, in DC current there is no change in the magnitude of current. Therefore, I versus T, if you draw a graph, the I taken on y-axis and T on x-axis, I remains constant, and therefore your graph is a line parallel to x-axis. Okay, there is no change in the quantity of current. Okay, and this is a DC current, but I can do something here. I can change the polarity. Look at what I am doing now. In case I change the polarity, because that being positive and this being negative, there is a change in the magnetic field produced there. Okay, I can turn it to this, I can change the polarity, except that there is nothing that I can do here, because the magnitude of current all the time remains the same in the circuit, producing the same magnetic field, of course, which doesn't vary with time. Okay, then I have a transformer. Okay, if you want to understand the idea of a transformer, generally we use an AC for it. Okay, and so I have taken an AC source, and the magnetic field is continuously changing. And what influence does it have here? See, there is one coil. Let us say this is a primary coil where the current is flowing. It's an AC current, but there is a secondary circuit and current is induced in this one. So, and how do we explain this actually? There is no current in the secondary circuit, only in the primary circuit. Okay, you have an AC source, this is the primary circuit, and you have a changing magnetic field, but current is induced in the secondary circuit. I just can show you how it's more actually. Now you can see it is better. Okay, you can see the bulb glowing because current is induced in that. And this is what we mean by a transformer, where you can increase the voltage or you can decrease the voltage. When you are generally increasing the voltage, I just call it a step-up transformer, and when the voltage is decreased, it is called a step-down transformer. So, you can use the transformer for either purposes. When you are getting your household current, there is a transformer, of course, outside your house or complex or whatever it is, and from there we reduce the voltage and we take it as our household supply. Okay, but sometimes it so happens once that electricity is produced, when you have to transmit that to a distant place, and generally we increase the voltage. There we use step-up transformers, and we have high voltage wires and high tension wires we call them, and current is taken to a distant place using these high tension wires, where a lot of amount of voltage is produced there, is converted into high voltage wires. So anyway, my point here is, this is a primary circuit. It all depends on the number of turns you have got, and whether you can increase the voltage or decrease the voltage. When you have more turns in the primary and less turns in the secondary, and generally we call it a step down transformer. I can increase and decrease the area also, of course. We can study that also. Generally this is the case where we have the bulb is glowing. What is the reason for that? Because the EMF, the current in the primary circuit can induce EMF in the secondary circuit. Okay, this is where we are using by increasing the voltage or decreasing the voltage, and this is what we mean by a transformer. And last of this Faraday's experiments, of course, which has got a direct application of Faraday's law, is a generator. Okay, so I have a magnet here, and if this magnet starts rotating, of course, about an axis, and eventually it produces an electric current. Okay, and that is what we mean by producing alternating current. And we have a bulb to check whether the current is produced or not, and the current produced in the coil, of course, it can be perceived by the bulb or galvanometer. And what happens when this magnet starts rotating? So that is our interest. So usually what happens, the water starts falling on that and making this move. Okay, and see the kinetic energy of the water which is falling from a greater height is making this turn and thus producing AC. You can see the field also. They are continuously changing, and you don't find this, it's not so conspicuous. And I increase the voltage, I increase the rotations per minute actually, like you can see the bulb glowing. But remember, this is AC in the circuit, and therefore the bulb glows with full brightness, and it becomes 0, and current starts in the opposite direction, again it becomes maximum. So that's what happens when you have an electric current, AC of course, and this is an AC generator. Okay, and when water is falling and this starts moving, and these are generally called turbines, we just rotate them, and this rotation can produce electric current. And that's what we see, of course, when you have a place where hydel electricity is produced. You have water coming from a big height, and when water falls, we make the turbines rotate, and from that rotation, that mechanical energy, we produce electric current. And therefore, when water is stored using dams and all, the level of water increases, and when you open the gates, the water falls from a great height, and that falling water can turn the turbines and produce electric current. This is general principle of like producing electric current is an AC generator. I just have a small important point I want to mention here, and I want to know the strength of the magnet at different locations. So I can use a field meter for that. Okay, and those of you who are familiar with the idea of flux density, you know that a magnet is strong near the poles. So if you take the field meter and keep it near the poles, you can see a huge amount as for 43.62 Gauss units. You got the magnetic field induction. As you go a little further, and it's increasing, and therefore, so we have established the fact that near the poles the magnetic field is very, very strong. But however, there is something which is more important. What happens if I want to measure it inside? It is furthermore, and it is even furthermore as you step inside. But therefore, I want to tell you there is a very important point here. A magnet has got at the end, as you see them, geometric poles, but actual pole of a magnet is slightly inside. And therefore, the real pole is not at the geometric end. It is not here at the end, what you see there. So, understand one thing. If you can draw the outline of this magnet and measure the length of this one, that can give you only the geometric length. Okay, that doesn't have to do anything. So, but real length of the magnet is 5/6 of the original length, and therefore real poles are inside. Magnetic poles are always inside the magnet, and they are not found. If at all you are finding a pole, it is only the geometric pole. Okay, now the same field meter, if I put somewhere here, it is just, I don't say it's inconsequential, but it's very insignificant. It is just 0.98 Gauss. Means lateral magnetism is not that significant. Its magnet is not strong on its sides. And somewhere near the poles, it is a huge value. Okay, that's somewhere around say 102, you can see there. That's a geometric pole. As you move inside, it's further more. Okay, that's what should be understood actually. So geometric poles are different, and actual poles of the magnet are different. Actual length of the magnet is smaller than the geometric length. So that's an important point, of course. So I am keen about knowing what's happening inside. Okay, if a magnet is taken and you have drawn the lines of force, you measured the field strength and all that, how about inside? So let me see what happens. So the magnetic lines of force start from the north pole and they move towards the south pole, outside the magnet. But within the magnet, it is again south to north. That's a closed loop, and that should be understood, of course, well. And therefore, the magnetic lines of force are found from north to south outside the magnet, but in the magnet, it is south to north. So that can be checked like this. You have here a magnetic compass, you put a dot and then again you start moving it, and you ultimately you are going to measure, you are going to trace, of course, and that's what happens. And the way it traces there, and you put a dot here again and you bring that the other pole there, south pole there, and again you convincingly you can bring it to this pole actually. Okay, so from the north the magnetic line of force starts and moves towards the south, but within the magnet it is exactly the opposite one. So if you can understand, you know what is happening inside a magnet. Thank you very much, and this is useful for magnetic effects of electric current.